Okay, so today what I want to discuss are the different BJT amplifier configurations. So there are three BJT amplifier configurations. We call them the common emitter configuration, the common base configuration, and the common collector configuration. The configuration is classified according to what the reference terminal of the BJT is with respect to the time varying signal. Now, for example, for the common emitter, okay, the common emitter, my emitter is my reference, my input is applied to the base, and my output is applied to the, or my output is obtained from the collector. So this is my common emitter. My emitter is my reference. So again, this is my common emitter. My input is applied at the base, and my output is obtained from my collector. In the common base, my base is the reference. So my base is the reference. My input is applied to the emitter, and my output is obtained from the collector. Okay. So this is your common base. And then in your common collector, my collector is my reference. Okay. So you try to imagine it this way. My collector is my reference. Okay. My input is applied to the base, and my output is obtained from the emitter. Again, the reference is with respect to the time varying input. With respect to the time varying input. That is the reference or the common terminal. The reference for the time varying input and the reference for the DC input may not be the same. It may not be the same. I'm going to show that later on. Okay, so let's start with a discussion of your common emitter amplifier. I already presented to you a very simple common emitter amplifier earlier in this module. Okay, so let's take a simple CE amplifier. Okay. So that looks something like this. So I have VCC. Let me call this R sub C, my collector resistance. My input is applied at my base, and my output is obtained rather from my collector. Okay, let's develop a relationship between my input and my output using the exponential model of the transistor. Okay. So this is a relationship between V in and V out using the transistor's exponential model. Okay, note that I cannot use the simplified model of the transistor here. The simplified model of the transistor just says that when conducting VBE is equal to 0.7. If I use that particular model, if I just say VBE equal to 0.7, then I won't have any V in with respect to V out because my V in will be fixed at VBE. So hindi ko pwedeng gamitin yung model na yon. We only use the simplified model of the transistor usually when making DC calculations, not when modeling variations in your base input. Okay, so you recall the improved exponential model where you have I sub C is equal to I of S e to the VBE over V of t minus 1 multiplied by 1 plus VCE over V of A. Okay, so this is our improved model, where the last refinement to the model was adding this term. I hope you recall what this term takes into consideration. You remember what V of A is? Can somebody just shout it out? Ano yung V of A? Anyone?
Early voltage, sir.
Yeah, that's your early voltage, no? So we added this particular term here to take into consideration the early effect. No? Yun yung ginawa natin in the last model. No? Now, for the meantime, I'm going to neglect this for the meantime. Okay. Now note that V of O, V out, is just VCC minus IC times RC. Right? So what is this? No, this is VCC minus, okay, IS e to the VBE over V of t minus 1, okay, multiplied by RC. Multiplied by RC. But note also that VBE is equal to VN, but VBE is equal to VN. So this is equal to VBE here. Okay. If I do a KVL, VN minus VBE minus 0 is equal to 0. So VBE is equal to VN. So finally, I have V out is equal to VCC minus I of S e to the VN over V of t minus 1 multiplied by RC. So this is now the relationship between VN and V out that I was trying to obtain. Okay, let's put some values here. Let's let let's say VCC equal to 10 volts. Let VCC equal to 10 volts. Let's say RC equal to 2K. IS equal to 1.5 times 10 to the minus 14 amperes. V of t equal to 26 millivolts. Okay. And let's say this is silicon, VC is at equal to 0.2 volts. Okay, I'm going to ask you to exercise your calculator. You already have the equation here. So this is just an exercise of your fingers on your calculator. Let's compute for the value of V out for different values of V in. So let's do it for V in equal to 0.4 volts, V in equal to 0.65 volts, and V in equal to 0.70 volts. So let's start with V in equal to 0.4 volts. Can somebody tell me what the value of V out is going to be? Pasok na lang nyo sa chat, no? When I get a certain number of responses, then we'll continue. So enter that in the chat. Round off nyo to 2 decimal places. Okay, please follow, no? Baka wala sa inyo gumagawa, hindi tayo, walang mangyayari sa atin dito. Okay, I already have one response. No other responses so far? Okay, maybe one more response. Okay, so far everybody got it right. So for V equal to 4 volts, my V out is equal to 10 volts. Okay, and that makes sense. Effectively, when V in is equal to 0.4 volts, we are not yet really making the base emitter junction conduct, because we know that the base emitter junction will conduct when the voltage increases to close to 0.7 volts. That is when the base emitter junction conducts. No? At least that's under the simplified model of the transistor. Hindi pa ito umaabot sa close to 0.7, and therefore my collector current will be equal to 0, and therefore my V out will be just be VCC, which is equal to 10 volts. Okay, okay, so next, ito, 0.65. 0.65. Can somebody tell me what V out is going to be? Ang bilis, no? Meron ka agad. Okay, so far so good. Okay, so V out is 7.84 volts. Okay, so actually at 0.65, for this particular transistor, nakikita natin na nag-conduct na yung base emitter. So this is a case where the transistor did not follow the 0.7, but it started conducting at about 0.65. So nag-conduct na yung base emitter. We already have a collector current flowing. Okay, and when a collector current flows, there's a voltage drop across RC, and therefore we expect V out now to be less than VCC. In other words, as V of in increases, you get I of C increasing, and V of out will be decreasing. So nakita na natin nangyayari yan dito, no? Okay, so last, no? V in equal to 0.7. Can you tell me what V out will be? Okay, I have one response, two responses, three. Let me wait for two more. 4, 5. Okay, the first 5 responses unfortunately were wrong. The 6th response is correct kay Jason. No? At V in equal to 0.7, actually your output will be 0.20 volts. Okay, so ingat kayo, no? Ingat kayo. Why is it 0.20 volts? Okay, remember what I said, as V in increases, V out will start to decrease. But what is the minimum possible value of V out? Ano yung minimum possible value of V out? Okay. Can somebody just shout it out? Bababa yung V out, ano, habang tumataas yung V in. Pero yung V out, hindi pwedeng bumaba lower than a certain value. And what is that value?
Sir, saturation po ng VCE, which is 0.2 volts.
That's right, exactly, no? So V out cannot become less than VCE sat, which is about 0.2 volts for silicon. Meaning to say, at this voltage, my transistor is actually saturated. It's already saturated. Like I said, for this particular example, maybe this is not a typical silicon, pero saturated na siya at 0.7. So here it is cut off. Here it is in active mode, and here it is saturated. Okay. Now, what do I want to do? No, I want to give you a good idea of how this performs as an amplifier. No? So to be able to characterize the behavior of this amplifier, it is helpful to obtain its transfer characteristics. Its transfer characteristics. And what is the transfer characteristic? We said that is V's of out versus V's of in. So I want to determine V's of out versus V's of in. Ano yung magiging itsura niyan? And I can do this. Using point by point calculation. In other words, gagawa ako ng graph V out, V in rather versus V out. Okay. And come up with a plot of what that graph is showing. Okay, now we already started that here. This is the start of our point by point calculation, but I actually did it here, no, using repeated calculations. So this is how the transfer characteristic of this simple common emitter amplifier looks like. Okay, let's take a look at the table. Okay, notice that from 0 to about 0.5 or even 0.6, okay, my transistor is cut off. My output is VCC or very close to VCC. So that's from here to here. Here I am cut off. On the other hand, when my input increases beyond 0.68, so dito sa 0.69, okay, my VCE already hits VCE sat and it will no longer decrease. So dito, I am in saturation. Okay. So this here is saturated. And then this area now is my active region. So from here to here, about here, this is my active region. Okay. This amplifier has a gain. How do we define gain? Gain is the rate of change of output with respect to input. So gain is actually d V out over d V in. The rate of change of your output with respect to your input. Okay. What is the gain in cutoff and in saturation? Can somebody tell me? Ano yung gain in cutoff and or in saturation? Ano yung gain dito? Tsaka ano yung gain dito?
Sir, 0 po.
That's right, it's 0. No? Because my output does not change with my input. Hindi nagbabago yung output ko habang gumagalaw yung input ko. My gain is 0. So the only region where I have a gain is actually here in the active region. Okay. Now note that, so gain is not equal to 0 in the active region, but also take note that the gain is not constant. Okay, what does this signify? This is the slope, right? This is the slope at the point. So this is slope. Right? So, for example, my gain here, let's say I'm considering this point, no? Itong point na to, let's say I'm taking into consideration that point. My gain there will be the slope of this line. On the other hand, if I'm considering, for example, this particular point, my gain here is the slope of this line. So that's for this point, slope nito. For this point, yung slope nito. Okay. Saan mas malaki yung gain ko? Doon sa point on the left or sa point on the right? Where is my gain higher? I'm talking about the magnitude of my gain. No? Let's consider magnitude of the gain. Is it higher the point on the left or the point on the right?
Sir, sa right po.
That's right, no? Yung linyang to mas steep, no? Mas nakatayo kaysa sa linyang to, no? And your slope increases when your line is steeper. So yung isa hindi masyado nakatayo, yung isa nakatayo, syempre yung slope nito mas malaki. And therefore my gain here is higher. So depending on my operating point, I will have a different gain. So hindi talaga constant yung gain mo in the active region. So your gain depends on your operating point. And so that is another basis. This is another basis for choosing your operating point. Remember your operating point or your Q point? Your operating point or your Q point is the point you want your bias circuit to establish when your input voltage is equal to 0. So, for example, we studied before that yung first choice mo usually would be somewhere in the middle of the active region. So, for example, if this is your active region from 0.6 to 0.7, your first choice would probably be in somewhere in the middle, no, 0.65. Why? Because the first basis would be the maximum output voltage swing. If you're somewhere in the middle, right, then you have a good input swing until it saturates and a good input swing until it cuts off. So that is one criteria. But sometimes you want to choose your operating point based on gain. For example, I want to choose my operating point here because I know that I have a higher gain here than if I choose my operating point here. Okay. Now, is that bad? No, is it bad to have an operating point here? No, it's not bad, as long as we make sure that our input signal does not bring us to saturation right away. And if your input signal variation is very small, it's possible that criteria will be met. For example, kung alam ko na yung input signal ko hindi lalampas ng let's say 0.01 volts, no? Dito mga 0.01 volts na yung mga difference. If my input signal I know does not go beyond 0.01 volts or 10 millivolts, then I know that my input will not saturate right away if I operate, for example, somewhere here or somewhere here. So the gain at the operating point is another basis for choosing your operating point. Now let's do a rough calculation of the gain. As VI goes from, let's say, 0.65 volts to, let's say, 0.66 volts. So this is a 10 millivolt range. So as I go from 0.65 to 0.66, so that's somewhere here, no? That's probably from this point, sorry, from this point to this point, what is my approximate gain? Okay, so gain will be equal to delta V out over delta V in. No? That will be my approximate gain. So let's look at that. No? At 0.65 to 0.66, my output changes from 7.84 to 6.83. So my change is 6.83 minus 7.84. And my change in input is 0.66 from 0.65. So if I compute this, this is going to give me minus 101. This is 1.01 volt. This is 0.01 volt. So 1.01 over 0.01 will give me minus 101. So note that this is a high gain, high value, high absolute value. Medyo mataas. That is the capability of the transistor to amplify. It can amplify an input signal up to in the hundreds of times, 101. Okay, and the reason for that is because of the base emitter diode. Because a very, very small change in your base emitter diode voltage will cause a large change in your collector current. Because you're now operating at that point of your base emitter diode curve where just a small amount of input voltage change will already cause a big amount of collector current change. Kaya ang taas ng gain. Okay, any questions with regard to the common emitter configuration? One more thing, no? The gain is negative. So from the point of view of your input signal, ano yung ibig sabihin ng negative gain? Anyone? What does the negative gain signify?
Sir, may phase shift po.
That's right. Well, what will the phase shift be?
180 degrees po.
180 degrees. In other words, as your input is increasing, your output will be decreasing, and as your input is decreasing, your output will be increasing. Your signal will be shifted 180 degrees. But that is not distorted, because as long as you can recover the information of the input at the output, then there is no distortion. Okay, any questions with respect to the common emitter amplifier? Let's go to the common base amplifier. So I said that common base amplifier, your base is your common terminal. You apply your input at the emitter and you get your output at the collector. So typically a simple. Okay, so let me draw a simple common base amplifier. Okay, so let's say this is VCC, RC. So my base is my common terminal. I apply my input to the emitter, so this is V in. And I get my output at the collector. That is V out. So again, what do I want to do? I want to get a relationship between V in and V out. I'm again going to use the exponential model of the transistor. Okay, I have V sub O is equal to, or V out rather, no? V out V out is equal to VCC minus IC times RC, where this is my collector current. So this is VCC minus, okay, what is IC? Again, let's neglect early effect. So this is IS e to the VBE over V of t minus 1 multiplied by RC. But what is VBE? Can somebody tell me what VBE is in terms of V in? Ito yung VBE ko, no? What is VBE in terms of V in? Anyone?
Sir, negative Pn.
That's right, no? VBE is just negative Vn, no? If you apply KVL to this loop, you're just going to see that Vn is equal to minus VBE. Therefore, I have now V out is VCC minus IS e to the minus V in over V of t minus 1 multiplied by RC. So here, for given values of V in, I can determine the value of V out. Okay, note that for the transistor to conduct, no, for the transistor to conduct, V in must be less than 0. Okay. Hindi magko-conduct ng transistor na to kung yung value ng V in is greater than 0. As a matter of fact, it is only when the value of V in is approaching 0.7 volts, maybe 0.65 volts or so. It's only when the value of V in is approaching negative 0.7 volts, okay, that this will conduct. Okay, so ulitin natin, no? Let's say this is the same transistor as the previous example. So VCC is equal to 10 volts. VCE SAT is equal to 0.2 volts. Ano nga ba? RC is equal to 2K. IS is equal to 1.5 times 10 to the minus 14 amperes. And then we said that PT is equal to 26 millivolts. Okay, so doon sa mga values kanina na ginamit natin, gagawin ko lang negative because V in has to be less than 0. So let's compute for V out for, okay, negative 0.4 volts, negative 0.65 volts, and negative 0.70 volts. So can you again please exercise your calculator and tell me ano yung magiging V in for V out for V in equal to negative 0.4 volts. So I'll take a look again at the chat. Okay, so far so good. Yes, no? So ito, just like in the common emitter, okay, V in is negative, but it is not negative enough. It is not negative enough to make this forward biased. Right? So your transistor will be cut off, IC will be approximately equal to 0, and V out will just be equal to VCC, which is 10 volts. Okay, next, no? Negative 0.65, ano yung V out? Ano yung V out for negative 0.65? Okay, good. Actually, magiging pareho to dun sa sagot natin kanina sa common emitter, no? Because you have the same value of I sub C flowing, the same R sub C, and therefore V out will be the same, no? This is 7.84 volts. Okay, dito ngayon, no? I want you to be careful here. Think about your answer very well. Okay, because you know what happens in the case of the common emitter amplifier earlier. You knew what happened when the input was 0.7. So what is the value of V out going to be here? Okay, I got an answer of 0.2. I want to see other answers first before I say correct or wrong. Think about it well. Okay, negative 4.78. Somewhere, a few more, a few more, no? Let's see if, okay, I'll already tell you, no? It's neither 0.2 nor negative 4.78. Okay, I got the correct answer from Ross. Ross, can you explain why you answered negative 0.5?
Ano po, from VN, I just added po yung VCE SAT.
That's right, no? That's right. Kasi, when Vn is equal to negative 0.7, nagsasaturate na to, no? Nagsasaturate na tong transistor na to. When this transistor is saturated, okay, sorry. When this transistor is saturated, the value of this VCE here, no, VCE will be equal to VCE SAT, right? Now V out, if you take a look at V out is V in plus VCE. So this is V in plus VCE. No? V out again is V in plus VCE, no? Which is negative 0.7 plus 0.2. So the answer is minus 0.5. Answer is minus 0.5 volts. Okay. What will happen if I make Vn equal to 0.8 volts? Can somebody tell me? Medyo trick question yon, no? What will happen if I make Vn equal to 0.8 volts? What will my V out be equal to? No, sorry, negative 0.8, no? Sorry, negative 0.8. Not positive 0.8. Okay. Theoretically, it should be negative 0.6, theoretically. No? Let me write that down. No? If Vn is equal to negative 0.8 volts, theoretically, V out, which is equal to Vn plus VCE SAT, will be equal to, okay, negative 0.6 volts. Okay, but actually, you're actually going to destroy the transistor. Okay, now let me explain why. If I apply negative 0.8 volts here, okay, I just looking at the base emitter diode. Okay, this is my base emitter diode. What am I doing? I'm applying, in effect, 0.8 volts across my base emitter diode. That is what is happening when I do this. Okay. If I take a look at the characteristics of my base emitter diode, so this is my base emitter diode. So let's say this is VBE. Ganyan yan, di ba? If this is silicon, anyway, this can be IB or IC, no? IC, let's just say IC, no? Okay, if this is silicon, approximately, what is this going to be? This is going to be 0.7 volts. Asan ang 0.8 dyan? Andito yung 0.8 volts. Where is my operating point going to be? My operating point, if I extend this curve up very, very high, very, very, very high, that is when my VBE will be equal to 0.8. And that is, okay, if you consider the steepness of this curve, that is a current that is already approaching infinity. And at that current, wala na, no? This diode is gone, or this transistor is gone. Okay. So if you had a transistor that could withstand that very, very large surge in current, okay, then your output would be -0.6, no, not -0.5, -0.6. But the truth of the matter is, you don't have a transistor that can withstand that large amount of current. So it's likened to this, no? We know that the forward conducting voltage of this is 0.7, but you're applying a voltage of 0.8. Okay, so you're forcing this voltage on something whose normal voltage drop is only about 0.7. It's actually an invalid circuit, right? But in actuality, what will happen is you're going to destroy this diode. Okay, but for all intents and purposes, your voltage, okay, should remain constant at about this value, no? Even if you apply a very large voltage, dapat it will remain constant at this value. So when Vn is greater in magnitude than 0.7, we just say that it stays, your output stays at 0.2. That's how we will treat this. Okay, so again, I completed the table. So this is my saturation. So hindi ko na pinakita dito na ano, no? Hindi ko na pinakita dito na bumababa to. Right? So theoretically this will go down, but let's just say that the diode voltage becomes about constant at about 0.7. Okay, even if your input is greater than -0.7. So this is saturated. Okay. Here, this is cut off. And then this is your active. Notice now that I plotted values of Vn, negative values from 0 to -0.8. Okay, my gain is dV out over dV in, no, which is approximately equal to delta V out over delta V in, of course, evaluated at the operating point. That has to be evaluated at the operating point. Now, taking a look at this graph, how does the gain of this amplifier compare with the gain of your common emitter amplifier? Can somebody tell me? So this is the gain of my common base amplifier. This is the gain of my common emitter amplifier. How does the gain compare? No? Let's talk about the absolute value of the gain. How does the gain compare? Anyone? Is it higher? Is it lower? That's all I want. No? Is it higher? Is it lower? Is it the same? No one wants to risk a guess. It looks the same, right? The magnitude of the gain looks the same. The slope is different. So here my gain is positive. Gain is positive. But the magnitude is comparable to my common emitter amplifier. But the gain, the only difference is the gain is positive. Can you see that? I hope you can see that. Okay, so you now have two options of amplifier. One is the common emitter, one is the common base. Okay. If you want to have positive gain, you choose the common base. If you want to have negative gain, you choose the common emitter. No? So remember, your gain is the slope. No? So the gain at this point is the slope. Okay? So this is your gain. Slope is your gain. Okay. Magnitude-wise, the common emitter and the common base have about the same magnitude. So they're comparable. Now, later on, you're going to be provided with additional criteria for choosing whether you want it to be a common emitter or a common base. No? Because another important parameter of your amplifier is what we call the input resistance. No? That's the input resistance or the input impedance that is seen by your input signal. No? Ano yung nararamdaman ng input signal na resistance na nakakabit sa kanya pag pinasok mo siya sa amplifier, pag kinabit mo siya sa amplifier. Okay, you will study more about that later on. Okay, but now you know the common emitter, negative gain, high negative gain, high gain, the common base, positive gain, also high gain. Any questions? Any questions so far? Okay, let's do now your common collector amplifier. Okay, so what is a simple common collector amplifier? Okay, so my common collector amplifier, my input is applied to my base. My output is obtained from my emitter. Now there has to be a resistor here. Okay, if there's no resistor there, then there will be no voltage at which I can measure my output across. No? Now my collector is actually connected to my VCC. Okay. Now from the perspective of an AC input, this is equivalent to ground. So that's what I was saying earlier, that the ground of your AC may not be the same as the ground of your DC. No? Now, this will be expounded upon more later on in the course. But why? Just to explain initially, no? Why is this equivalent to a ground? Well, when we analyze amplifier circuits, we usually separate it. We separate the DC component from the AC component. And then I mentioned earlier, we actually use the principle of superposition. No? We take the DC component acting by itself, and that's what we use to establish the bias point. And then we take the AC component acting by itself. That's what causes the output voltage to change. And then we use superposition. If we take the AC component acting by itself, that is, we suppress the DC, then your DC sources are already short circuits. So if this is a power supply, VCC, and we're only taking into consideration the AC component of your signals, then your power supply is already equivalent to a short circuit because we already suppress it. No? This is because of superposition. That is why, even if this is VCC, from the perspective of your AC signal, that is like ground. And this is another configuration of your common collector amplifier. Okay, so again, we're going to try to develop a relationship relating V in and V out. So what is V out? V out is equal to V in minus VBE. Let's mention that this way. No? So take note that V out does not even depend on RE. No? Not yet, at least. No? Not yet. It's just V in minus VBE. Okay, now we know that I sub C, so this is I sub C, based on our exponential model of the transistor, this is I sub S e to the VBE over V sub t minus 1. Again, we will neglect early effect. Okay. This is approximately equal to I sub S e to the VBE over V sub t, because under normal operating conditions, itong -1 will be very much smaller than e to the VBE over V sub t. No? Let's just assume that is true all the time. So this is the approximate value of I sub S. Okay. I can compute for VBE. Okay, this is equal to V sub t ln of I sub C over I sub S. Now for large beta, okay, you have I sub E is approximately equal to I sub C. No? If you will recall, I sub E is equal to beta IC over 1 plus beta. Sorry, no. I sub E is 1 plus beta IC over beta. No? That's I sub E. I sub E is equal to beta plus 1 over beta times I sub C. And if beta is large, this is approximately equal to 1. That's why I sub C is approximately equal to I sub E. And I sub E is also V out over R sub E. If the voltage across this resistor is V out, then I sub E is just V out over R sub E. Therefore, from this equation, okay, what is V out? V out, this is equal to V in minus VT ln of I sub C, but I sub C is approximately equal to I sub E. No? So I have V out over R sub E times I sub S. So this is an equation that relates V in to V out. No? So let me ask you, if I give you a value of V in, would you be able to compute for V out? Anyone? Bigyan kitang value ng V in, can you compute for V out? Anyone?
Sir, try lang.
What do you mean try
I
lang?
think opo.
How?
Solve function po ba?
Okay, that's right, ano? Nung panahon namin, wala kaming solve function sa calculator. No, in fact, I'm ashamed to admit this, but when I entered college, there wasn't even a scientific calculator, no, for function calculator lang. So panahon namin, wala kaming scientific calculator. Ngayon, meron ng solve function. We would have to do this actually by iteration. No, we would solve this problem by iteration. Okay, but now you have the solve function, so you can, if I give you a value v in, you should be able to compute for the value of v out. Okay. Now we know that this transistor will not start conducting until v in overcomes, no, the forward conducting voltage of the transistor, which is about 0.7. No? But just the same, let's use this equation to come up with various values of v out for particular values of v in. No? So, okay. So sabihin natin, no? Same transistor. Okay, so VCC also equal to 10 volts. Sabihin natin RE ngayon is equal to 2K. So IS is 1.5 times 10 to the minus 14 amperes. VT equal to 26 millivolts. Ano pa ba? Yeah, VCE active, VCE sat equal to 0.2 volts. Okay, so can you tell me, no? For these values of V in, ano yung magiging values ng V out natin? So let's start with 0.4. And then let me go to 5.0 volts. And then let me go to 12 volts. So umpisahin natin sa 0.4. No? What will be the value of V out? So again, I'll check the chat. Ano? Tama ba? Is that right? No, we're determining V out, no? V out. In other words, you use this particular equation to determine V out for a given value of V in. Okay. Yeah, it's going to be quite small. No? It's going to be quite small. Right? I don't have the exact figure here, but I'm guessing tama yung ano, no? Yung in the range of 0.14 millivolts, no? Okay, it's so small. Okay, it's so small because essentially this transistor is cut off. No, yung 0.4 volts is not, V in equal to 0.4 volts is not enough to really make this base emitter diode start conducting. So if it's cut off, IE is approximately equal to 0. So V out will be approximately equal to 0. So this will be approximately equal to 0. So you get your cut off. Okay. Okay, then we can compute it for V in equal to 5, V in equal to 12. I'll skip that now. Okay, let me just show you what I came out with. So this is what I came out with. Okay. So, okay, you will notice that here, basically I'm cut off. Okay. Here I am saturated. Then here I am in the active region. Okay. Bakit 9.8 volt siya kapag saturated? When transistor is saturated, V out is equal to 9.8 volts. Well, the reason is this. No? So ito yung VCC. Okay. Andito yung V out ko. Okay, this is RE. This is V in. Okay, as V in increases, V out increases. No? Habang lumalaki yung V in, lumalaki yung V out. Kasi habang lumalaki yung V in, lumalaki yung value ng IC, lalaki din yung value ng IE. Pag malaki yung value ng IE, malaki yung voltage across RE. So tumataas yung V out. Okay, pag tumataas yung V out, anong ibig sabihin? Itong VCE lumiliit, ano? So as V in increases, VCE decreases. Again, no? Why? As V in increases, V out increases, and therefore VCE should decrease. Okay, but what is the minimum possible value of VCE? No? VCE minimum will be VCE SAT, right? Your VCE, the voltage from collector emitter, cannot be smaller than VCE SAT, which is equal to 0.2. No? And in saturation, V out will now be VCC minus VCE SAT. Itong output voltage na to will just be VCC minus the voltage from my collector to emitter, which is VCE SAT. So this is 10 minus 0.2. So I'm just going to get 9.8 volts. Right? That is why this is 9.8 volts. Okay, examining the graph. Okay, so again, we know now that this is a cut off. Sorry, no, this is cut off. Okay, this is now saturated. Examining the graph, what is the gain? Can you tell me approximately what the gain is? Sigaw na lang nyo. What is the gain?
Sir, is it 1 po?
Yeah, no? If you take a look at the slope of this. The slope of this is approximately equal to 1. Which is your gain? No? Right? And that is the characteristic of your common collector. Itong amplifier na to, we also call this your emitter follower. Okay. Why is it called their emitter follower? Because the emitter, the voltage at the emitter follows the input. No? Again, this is from the perspective of AC. No? This is from the perspective of your AC input signal. Kung ano man yung input dito, yun din yung value ng output dito. So your emitter, gaya-gaya lang yung emitter natin, ano? Yung kung ano man yung nakikita niya sa input, ginagaya lang niya sa output. You also sometimes call this a buffer. And I think you already are familiar with the term buffer. You learned that when you studied op-amps. A buffer is a circuit that isolates your input source from your load. No, you don't want your load to attenuate your input source, and therefore you put a buffer in between your input source and your load. So that is what this circuit also does. It isolates the input source from the load. The load presumably is going to be R sub E here. No? This is going to be our load. Okay? Meaning to say, kung ano man yung input natin dito, yun din yung magiging output natin across the load. Okay? And the load will not attenuate your input. Kasi kung yung load ko-connect natin direkto sa input, your input will sometimes suffer. No? It will suffer a voltage drop because of its internal resistance. Yeah, you can also call it a voltage follower. That's right. No? Somebody asked if it can also be called a voltage follower. That's right. Okay, now I have another graph here. No? And this other graph, ang ginawa ko, okay, I wanted to see whether I could have applied the simplified model of the transistor. So remember, we've been talking about two models of the transistor so far. One is the exponential model, which we usually use when we do calculations where our input is changing. And the other is your simplified model, which we usually use when we're doing DC calculations. For example, when we're calculating the bias point. And in the simplified model of the transistor, we just say that VBE is equal to 0.7 volts in active mode. That's what we do. Okay. Now this is the output if I had used the simplified model. No? If I use the simplified model, so VBE active is just equal to 0.7 volts. Okay, and therefore V out will just be V in minus 0.7 volts. So kung ano man yung value ng V in ko when it is active, my V out is just that value minus 0.7. And if you take a look at the values, they're actually very close to each other. Pag tinignan mo, malapit, ano? 9.3, 9.31, no? 8.32, 8.3, 7.32, 7.3, 6.32, 6.3. So they're actually very close to each other. So all I wanted to point out here was if I had used the simplified model in my analysis from the beginning, I would have come up with something with very little error. Yun lang, no? Yun lang ang gusto kong i-point out dito sa slide na to. No? Okay, are there any questions? Any questions? Okay, so we have three models. No, three models of three transistor configurations: common emitter, common collector, common base. Okay, how do we apply now the input signal? Okay, so the first step in designing an amplifier circuit is always designing the biasing circuit. So we always start with the biasing circuit. So this is used to establish the operating point. The Q point or the operating point. And we studied several biasing circuits. So let's say, excuse me. So let's say we use the voltage divider bias. No? So example, let's say we use the voltage divider bias. Or sometimes we call this the self-biasing circuit. So how does that look like? If you recall, so you have VCC, and then you have RC, RE, R1, R2. Okay. In the common emitter amplifier, where do we apply our signal? We apply our signal to the base, right? But what we do is we capacitively couple the input signal. So I explained that earlier. Why do we capacitively couple it? So this is my input. This is V. Now this is small I. I apply that through a capacitor because I want this to isolate my input from my DC source. This is equivalent to an open circuit for DC. So kung ano man yung DC voltage na nanggagaling dito sa VCC, hindi niya maapekto tong piece of I, no? Because this will be an open circuit for DC, and therefore my bias point will only be established by VCC. No? On the other hand, okay, this capacitor is supposed to approximate a short circuit at the frequency of my input. Okay, and then using the principle of superposition, okay, this is now going to be applied at my base emitter on top of the operating point established by this resistor network, R1, R2. Okay, so this is how you apply your input signal for your common emitter, and then where do we get the output? We get the output here. So this is now V capital OUT. So this is for your common emitter output. Okay, for the common base, we start with the same biasing circuit. Okay, so this is RE. This is R1, R2. So that's the same biasing circuit. So we use this to establish the operating point. Okay. Where is my output? My output is still here. So this is my output. So this is the common base. Again, this is common base. Now, where do I apply my input? I apply my input at the emitter. So this is now how I apply my input. Okay. So again, this previous circuit establishes the operating point. And then now, this is now how I superimpose my input here on the emitter terminal. And that will cause changes in my output. So that is my common base. And for all intents and purposes, this is equivalent to a ground for the DC, for the AC. Okay, for the AC. For the same reason that I explained earlier dun sa common collector. Now, what about sa common collector? Okay. My common collector, I still apply the input to the base, but now my output will be here. So this is my output for my common collector. So this is for the common emitter and the common collector. Okay. So this is for the voltage divider bias circuit. Any questions? So I just wanted to show you how the inputs and outputs are applied in an actual amplifier after the bias point has been established. Okay, and then just a few last notes. Okay, how did I characterize my amplifier? Okay, what did I do? In characterizing my amplifier, what did I do? I created these tables. These are tables of output versus input. And notice what I did. I used point-by-point calculations, which are very tedious. Okay. Very tedious to make these point-by-point calculations. And in getting my gain, I had to do also point-by-point calculation of gain. No? If I want to get my gain, I have to do a point-by-point calculation here because there is no function that I can use, for example, to get a derivative here. No? Okay. Well, maybe I could. No. Maybe I could have. Well, actually, I could have. No. Pwede nga palang ano, no? Pwede nga palang kunin yung derivative of V out with respect to V in dito. So it's possible. Sorry, I erased that, no? But just the same, no? Getting the output, I did a point-by-point calculation using this equation. So this is for the common base. I had an equation for the common emitter, for the common collector, which is based on a large signal model. The large signal model of my transistor, which in this particular case is the exponential model. So that's what I wanted to mention here, no? The method used in analyzing the various amplifier configurations presented was point-by-point analysis using the large signal transistor models, which happen to be nonlinear. Okay, fortunately, from this point onward, that is not how you will be analyzing transistor circuits. From this point onwards, you will be using linear techniques to analyze amplifier circuits, to analyze transistor amplifier circuits. So you will not use this point-by-point technique. You will use linear techniques. But for you to be able to use linear analysis, you have to have a linear model. And our linear model is going to be the small signal model of our transistor. So next Thursday, what I'm going to introduce to you is the small signal model of the transistor, which when your input is confined to small changes, is a valid model for your transistor. And because it is linear, you can now use all of the tools for linear analysis that you studied in 1, 2, 3 in analyzing these circuits. So it's parallel to what we did when we studied the small signal model of the diode. You could use your 1, 2, 3 circuit techniques to analyze the circuit. Okay, so that is all I wanted to cover for today. Are there any questions? Any questions? Okay, so if there are no questions, yeah, I'll close the session again when the last person leaves. Okay, so thank you.
Thank you po, sir. See you po
Thank you,
next week,
sir.
sir.
Thank
Okay.
you, sir.
So next week, next week we will be face to face.
And then, sir, yung head po namin susundin. Like, for example, kami pong 2:30 kami ganun, papasok.
Yes. Actually, may extra capacity yung 1 to 2:30 kasi malaki yung kwarto, no? If you prefer to use the 1 to 2:30 session, you have to tell me kasi may mga requests also for sit-in from other classes that I accommodated already, no? So baka lumampas sa capacity. But maybe after a few weeks, makikita ko kung ano yung loading ng various classes, and it might be possible to accommodate the 2:30 to 4 in the 1 to 2:30 class, no? Pero yung the other way around mahirap kasi yung 2:30 to 4 mas maliit yung kwarto. So hindi ma-accommodate lahat ng tao because of the social distancing which we have to conform to.
Okay po, sir. Noted po.
Okay.
Pasabihan na lang po namin kayo kapag po magsisit-in kami sa 1 o'clock para double retention. Para 2 klase attendance. Sige po, sir. Salamat po.
Masipag ka kung gano'n, no?
Sir, mahina lang po yung retention ko kaya po 2 beses ko pinapanood yung mga videos ninyo.
Okay.
Po. Thank you po.
Okay.
Thank you po, sir.
Okay, you're welcome.
Thank you, sir.
Yes, Rondel.
Sir, tanong ko lang po yung sa prob set. Pwede yung may table po ba na problems, pwedeng sagot na lang po or kailangan din mo ipakita yung solution doon?
Kailangan pakita mo yung solution, no? Kasi syempre may assumptions per problem that you have to validate, no? Basically.
Okay po. Thank you, sir.
Okay.